Today we're going to start a brand new topic, thermal physics. So what is thermal physics? All right, so we want to write down what it is. It usually covers three areas. The first is thermodynamics. And thermodynamics is a study of how the properties of macroscopic objects are related. So this is how properties of macroscopic objects are related. It is truly remarkable how much one can get without knowing what matter is made of. So this was developed in probably the 1800s, and they really weren't even sure what matter was made of. The idea of an atom or molecule was not really that well known. That really wasn't settled on until later in the 1800s and early 1900s. And this theory does not rely on that at all. You don't need to know anything about what matter is made of. All you need to know is that there's different kinds of matter. So like there's air, there's water, there's ice, and they can recognize that ice and water were made of the same stuff. All right, that they can recognize. But they didn't know what it was made of. And thermodynamics tells you how different properties are related. And it does this with only 2 or 3 laws. It's truly remarkable. So most of what we will do is thermodynamics. The second subject is the kinetic theory of gases. And what this does is it uses classical mechanics to derive certain results for gases. So it uses classical mechanics. That's what you've learned to derive some results for gases. So those are the first 2. And then the third subject, which has really blossomed a lot in the last 30 years, mostly because of the existence of computers, is statistical. And what this does is explains thermodynamic results using microscopic, so that's like atoms and molecules, so microscopic models of matter, and using probability theory. And we'll do a little bit with this. So this has been an extremely powerful model of nature, statistical mechanics. This whole approach, the idea of thermodynamics as kind of a high-level theory based on empirical observations, and then statistical mechanics as a lower level theory that explains thermodynamics, is frequently used as the paradigm, the example of reductionism in science. Right? Namely, we reduce one theory to a more fundamental theory underneath. And this is probably the best example. When philosophers talk about reductionism, they almost always use this example because it's so powerful and works so well. Other examples are deriving, let's say, solid-state physics from quantum mechanics. Quantum mechanics is a lower level theory. Solid-state is the sub-theory of solids. Or nuclear physics, trying to understand how nuclei work by understanding the quantum mechanics of protons and neutrons and even quarks inside a nucleus. All right? So there are other examples, but this is by far the most common and illustrative example of how reductionism works in science. There's been some critiques of reductionism. I think some of those critiques are valid. All right? There's some sense in which certain ideas don't really reduce down to a fundamental level. There's something at the higher level that's sort of fundamental. And I could individually talk to you if you're interested, but I won't do that here. It's pretty subtle, and it's not agreed upon by everybody. But there's no question that using reductionism has advanced not only physics, but chemistry, biology, and maybe some other subjects. It's more problematic outside the physical sciences. Some people argue, for instance, that trying to use reductionism in psychology is problematic, and may be. So that is what we're going to be talking about. Okay? We'll spend most of our time on thermodynamics. I'm going to just use the kinetic theory of gases today. It's probably the last time I'll really use it to derive a certain result for gases. And then we'll use statistical mechanics, maybe a little bit over the next few days, but mostly near the end of the course. Right? And I will be doing some things here that are definitely not really treated in the textbook. Okay. So let's start out with the kinetic theory. All right. I'm going to use this to derive two main results for what are called ideal gases. So this is an important concept. What is an ideal gas? So this is a model of dilute gases. What does dilute mean? Yeah, so the concentration is low. All right. In practice, what that means is you have the distance between any two particles is large relative to the size of those particles. All right? That distance is sometimes called the mean free path. Right? It's the path that a particle can move without interacting with other particles. All right? It's large. All right? So that's what we mean by dilute gases. The air in this room is a very good example of a dilute gas. And the ideal gas law, the ideal gas model, works very well for the air in this room. So an example would be air. All right, so the air in this room is an example of a dilute gas for which the ideal gas model works well. What is that model? What's in it? There are two ideas. One, particles are point particles. They have no size. All right, so that's one key idea. The second idea is there is no potential energy of interaction. So there's no potential energy in the system. All right, that's not strictly correct, but to a very good approximation, it's very accurate. So the air in this room, it does have internal energy. So what do we mean by internal energy? I just mean the energy of the particles in this room, right? So the internal energy is all kinetic energy for the ideal gas model. Okay, so that's very important. The internal energy of an ideal gas is all kinetic energy. And just to remind you, kinetic energy equals 1/2 mv squared. Right? So that's the kinetic energy. So this model is very peculiar because despite the fact that the particles have no size and there is no potential energy of interaction, we assume that somehow the particles' velocities change. Somehow they change. Some of that change is because it bounces off a wall, so the velocities will change. But also, somehow they knock into each other and exchange energy. But we don't know anything about how that happens, and we assume that any interaction energy, any potential energy, is negligible. So that's kind of an odd model. All right? But it's amazing how well we can do with it. All right. So what are the consequences of this model? The result is this formula. And this is the formula that you all have to know. This is called the ideal gas equation of state. This is the ideal gas equation of state. All right, what are the symbols? This is pressure. This is volume. This is number of molecules. This is temperature, and it's in the Kelvin scale. You cannot use Celsius or centigrade in this formula. And even worse, you cannot use Fahrenheit. That's really bad. Okay. Not that any of you would do that. Only Americans would think of that. Okay? So that's temperature, Kelvin scale. This K here is called Boltzmann's constant. All right? I'm going to get rid of it. It's not this K. It's a different one. The book puts a little b at the end. I just don't like doing that. So this is equal to 1.38 times 10 to the minus 23 joules per Kelvin. All right, so joules per degree Kelvin, if you want to do that. I think I got that right. All right, we're not done yet. N is the number of moles. So all of you, everybody here probably took chemistry at some point, right, in high school. They tell you what a mole is? Yeah? Well, I'm not going to tell you much more, so you better look it up if you don't remember what it is. Or in our textbook, it probably tells you. And then R is the gas constant, and it equals 8.314 joules per mole per degree Kelvin. So I imagine the chemists have more difficulty with powers of 10, so they like to use this. That's probably not. That's just making a little joke there. They like moles. All right? Moles tells you basically how much of a substance you have. So clearly, NR is the same as this capital N times K. They're the same thing. And they're related by what's called Avogadro's number. All right, so I can write that down. N Avogadro times K equals R. And that leads to this is 6.022, something like that, 10 to the 23rd molecules. It's a large number of molecules. It's called Avogadro's number. So it's the number of molecules in a mole. All right. So that's the formula. Where did it come from? Where did the ideal gas law come from? Well, the people who first discovered it, like Charles, I think, was one, and Boyle was another, and somebody else. They didn't know kinetic theory. They didn't know how to use it. They developed it purely from experiment. They kept a gas in a container, and they pressed on it, and they can measure the pressure. What's pressure? Force per unit area. So that's something they knew how to measure. So they can measure the pressure, they can measure the volume, and they can see that if they kept everything else constant, that the pressure was inversely proportional to the volume. P goes as 1 over V if T equals a constant. All right? And then I'll talk a little bit about how they developed the concept of temperature. But first, I'm going to derive this result from kinetic theory. All right, so let's do that. Let's start over here. So the basic idea is the following. Let's imagine I have a cube. A cube sitting in space. Let's call this, how about this is the x direction? No. We usually call this x, y, and z. All right? So we're going to do that. And I'm going to look at the particles hitting this wall. All right? So this is an L by L by L cubed. All right? So the volume is L cubed. So you have L by L by L. So that's just to make all the calculations simple. All right, so what happens when a particle hits this wall? So you have a gas molecule inside the box, and somehow it hits this wall. What's going to happen? Let me do an example. What happened? It bounces back. Okay. Let's assume, it's a pretty good assumption, that it bounces back. You know, the angle of reflection equals the angle of incidence. All right? So what happens is particle hits wall, and we'll use the YZ plane. So Vx goes to minus Vx. The x component changes sign. The x component's going that way initially, and it's coming back this way. Elastic collision. Same magnitude, opposite direction. That is the only component that's going to contribute to the pressure on the wall. Right? The y and z components don't contribute because they're parallel to the wall, not perpendicular. So what is the change in momentum? Right? So what's the change in momentum for that particle? 2, very good. 2 mvx, very good. Right, so the change in momentum is 2 mvx. All right. So, we're using classical mechanics. You guys should be experts on that by now. We spent the last 15 weeks or so almost exclusively using classical mechanics. Any idea what theorem we want to use from classical mechanics? Because we want to get out a force on that wall. How are we going to get that from the change in momentum? Well, we have a theorem. The something momentum theorem. Anyone remember that? What's the word? I think I heard it. Impulse. So we have the impulse momentum theorem. All right. And what that says is the change in momentum is equal to the average force delta t. All right, so it's really an integral, but we can just replace that integral by an average force times delta t. All right, we have the left-hand side. This is 2 mvx. And we don't know, this is what we want to find, because that's going to tell us the pressure. All right? That's the average force in the x direction. What are we going to use for delta t? Well, we want the average over time. This particle has a velocity v sub x, right? It's only going to hit that wall occasionally. When is it going to next hit the wall? What's the next time it's going to hit the wall? That'll tell us what the delta t is. All right, so there's one little impulse on the wall every delta t seconds. When will it next hit the wall? Well, my particle goes like that, right, comes back. What happens after it comes back? What is it going to do next? The particle hits that wall. It what? It's going to hit the other wall on the other side. How far away is that wall? L. How much time will it take to get back to the original wall? 2L divided by what? Vx. There we go. Very good. All right, so the 2's cancel, and we have F av equals m Vx squared. Pretty good. All right. Now we can relate this is for one particle. One particle. For n particles, we get F av total. The net force on that wall due to all the particles is going to equal m Vx squared. And I have to put an average over it, because not every particle is going to have the same x velocity. Some will be slower than others. But on average, I can do that. And then I can multiply by n. OK? Everybody good with that? And then the force, how is the force related to the pressure? How do you get the force? How do you get the pressure from the force? Pressure is, yeah, force per unit area, force over area. All right, so pressure is F total over the area. What is the area of that side? What is that area? L squared. Oh, I forgot something. MVL squared. There's an L somewhere. Where is it? Over here. Right? Somebody should have told me about that. All right, so I have mvx squared divided by L. All right, so I don't run out of room, so let me write this over here. So I finally get P times V, right? L cubed is V, is equal to mvx squared half times n. All right, so let me write all this down. I have an n there, and then an average there. OK, everybody look good? So this is what we get. All right, we derived that. It's pretty accurate. Works for the ideal gas. There's only kinetic energy in there. Nothing, no potential energy, nothing. At this point, we're stuck. There's nothing we can do using classical mechanics. Classical mechanics gives us no further insight. So what do? You make a hypothesis, an assumption. All right, so in kinetic theory, we set mvx squared average equal to kt. All right, we just make up that it's kt. There's nothing I could say or do or say anything to derive that. Not from kinetic theory, not from classical mechanics. All right, so we just set that. We set it this way so that it'll be consistent with experiments. Okay, so that's the key idea. So this gives us PV equals NKT. Okay, so we have that result. We also have one more result, that the average energy is 1/2 mvx squared average plus the same thing in the y direction plus the same thing in the z direction. And then you just multiply by n. And so you get, it's 3/2 NKT. All right, so kinetic theory tells us what the kinetic energy is compared to the internal energy. So the internal energy is 3/2 NKT, and this is just looking at translation. Just looking, if the molecules rotate or if they vibrate, like oxygen vibrates, that's not included in here. You have to add that extra. All right? So these are the two results. This one up here and this one down here are the two main results that you get from kinetic theory. Now, I am going to now make an opinion. I do not want to say, I don't like saying, I think our textbook might say, that this is the definition of temperature. I hate that. Right? I think that's bad for two reasons. That's a bad definition of temperature. Reason number one, it's not generally true. That's a good enough reason. At low temperatures, that does not work. The mean kinetic energy is not equal proportional to the temperature. It has some other relationship. It's more complicated. So that as a definition only works at high temperatures, at room temperature, things like that. So that's one reason I don't like to call it a definition. But there's a second reason, maybe even more important. It gives you no idea why we have temperature in the first place. Why do we need temperature? Why do we need that quantity? Why do we spend so much time figuring out how to build thermometers that measure temperature? Well, that formula tells you nothing about that. It doesn't tell you what the role of temperature is. All right? What is the role of temperature? Why do we have that as a quantity? All right? So that is the key to all thermodynamics. Why introduce temperature? And we'll get to that later, but I'll give you a little preview right now. All right? And the preview is this chair at the same temperature as this table? How about the floor? Yeah. How about the air? They're all at the same temperature. But this he's a hot head, right? He's got a hot head, right? Is his temperature the same as this table? No. So what's happening? What's happening? Does the air in the room give energy to him, or does he give energy to the air? He's heating up the air. In fact, this room is a teeny bit warmer than it would be if you weren't here, if all of you weren't here. Classical mechanics tells you nothing about why energy goes from hot to cold. That comes from temperature, the concept of temperature. That's why we need temperature. It tells us which way energy flows. And we all know it flows from a hotter object to a colder, right? This has been sitting out a while. Sitting out. Touch that. All right, now touch this. Which one's warmer? Which one's warmer? This? Really? This has been sitting out all the time, for over an hour? Touch two things. Everything on your desk. Start touching things. Which ones are warmer and which ones are colder? Well, I'm going to tell you a secret. They're all at the same temperature. If they've been sitting around long enough, they come to equilibrium with the air in the room. Why do they feel differently? It's not because they're at different temperatures. It's because of another property, which we're not going to talk about, called conduction, heat conductivity. Metal conducts heat energy, takes in energy quicker than this piece of chalk. And you you are a lousy thermometer. You are not very good thermometers because you make mistakes in what is hot and what is cold. Because you base your estimate on the conductivity of energy, not on the actual temperature. So I have a great example of this that I showed to a bunch of 4-year-olds, not 4-year-olds, 8-year-olds in a class. I took a piece of solid iron, a really thick piece of solid iron, and then a piece of wood. And I put an ice cube on top of each. What do you think happened? The kids were astounded by what happened, actually. They'd never seen this in their life. What do you think happened? Well, the ice cube on the piece of wood, it just sat there. Nothing happened. The ice cube on the piece of iron, it turned to water very quickly. It just started spewing out, right? It just melted incredibly fast. Even though the iron and the wood had been sitting in that room for hours and were at exactly the same temperature. Why did the ice melt when on the iron? Because the iron conducts energy much quicker. All right? So it could give energy to the ice cube a lot easier. That was due to conductivity, not due to just the temperature difference. All right? So you have to separate out those two ideas in real experiments. All right? We will not have to worry about this in this course because we will always be assuming nice conductivity and things work well. Okay. All right, so what I want to do now is just to give you a little idea about how the ideal gas law came about. All right, how could one figure that out without knowing what matter is made of, what gases are made of? All right, so as I mentioned, you can find out that at a constant temperature, P times V is a constant. And then they realized if they put more gas in there, like they can probably weigh how much gas is in there, they found out that the pressure, P times V, depended on how much gas is in there. So that's either the capital N or the little n. And somehow, they would have to define some standard mass. And that's what they might use a mole. I don't know how they historically did that. So then the only real question is, how do you deal with the temperature scale? How do you define temperature? All right, using this. So the key idea is they take your system, P and V, and they embed it in ice water. And they say that temperature equals 0 degrees centigrade. And then they take the same thing, all right, and they put it in boiling water. Right? So they can see the water boiling, bubbles coming out. So they know it's boiling. And they say that is 100 degrees centigrade. They measure P here, V there, PV, and the change in PV they define to be, for this case, 100 times, let's say, NR, or 100 times nk. So they make that definition. So that tells us what each degree is. When we say one degree is bigger than another, it means the delta PV at one temperature must be 1 degree bigger than another. So that gives you the Celsius scale. But clearly there's a problem here, because if I plotted this using centigrade, so if I plotted PV versus T centigrade, it's not going to go to 0 at this T equals 0, right? It's going to have, at T equals 0, there's a certain value there. Okay? That's pretty obvious, right? Because P times V at T equals 0 degrees centigrade is not 0. Also, just one thing I forgot to say. I'm talking about the pressure inside the gas. To measure that, I have to worry about the pressure outside. So when I push on the gas with some force, that's a force plus atmospheric pressure times area. So I have to separate out the atmospheric pressure times the area in order to get the pressure inside the gas. So you can extrapolate this down here. And if you do that, you get roughly minus 273 degrees. So PV goes to 0 at minus 273 degrees. All right? So we define temperature in Kelvin as equal to temperature in centigrade plus 273 degrees. It's actually 273.15. I think that's what it is. Yeah, 273.15. All right, so that's how we define the Kelvin scale. All right, and that's what's universally used. Now, there's a slight difference. I can't remember what the issue is between centigrade and Celsius. I think the difference is 0.01 degrees. I'm not going to worry about that. If you're interested in that, you can read about it. All right, it has to do with historically how the scales were defined. But for our purposes, you could just use 273. We're not going to be more accurate than that. And it's pretty hard to get much more accurate. OK. So that is the temperature scale. So once you do that, then all you got to do is you can figure out what this is, NR, NK. And you have to figure out some standard mass to put in there in order to get the right answer. All right? And what has been standard up until, I think, a couple weeks ago, literally, is 12 grams of carbon-12, I believe it is. 12 grams of carbon-12 is defined as 1 mole. All right? And that has been the standard up until, I think, a few weeks ago. I read an article that they decided to scrap that, and they're now using some other definition that's based on, the mass of a proton or something like that. Some other combination of fundamental constants. But for our purposes, think of a mole as 12 grams of carbon. That's 1 mole. So the number of particles in 12 moles, 12 grams of carbon, is Avogadro's number. That's the number of atoms in that mole. So what is a thermometer? Here's a thermometer, right? And it measures, right? So the key idea of a thermometer is the following. Every thermometer that I know of is based on knowing how some property of the thermometer depends on temperature. So the key here is some property of the thermometer depends on, so some examples. I don't even know if anyone ever seen a mercury thermometer, or they're totally non-existent anymore. You know what a mercury thermometer is? That's what I had when I was growing up. And this one is a little tube with a little bit of mercury in it. Mercury is the only metal that is a liquid at room temperature. When it heats up, the mercury expands. All right? So by looking at how much it expands, you can tell what temperature it is. That's how a mercury thermometer. So it works by liquid mercury expands as T goes up. All right. Another one that I used as an undergraduate is called a thermistor. And this is the electrical resistance. Depends on temperature. All right, it grows as T goes up. All right. Another example is thermocouple, I think it's called. All right, so this is two dissimilar metals, metals, all right, and the voltage between the two, 1T. All right. So there are many examples of thermometers. Nowadays, these digital thermometers, I don't know what they use. You can look it up what they use. It's probably some complicated thing. So this property depends on temperature, and then you have to calibrate that property. Then you have to calibrate the thermometer to give the same result as ideal gas law. So you basically calibrate these thermometers so it gives the right temperature for the ideal gas law. So the key here is you take a thermometer, it has to interact with the substance that you're measuring. And through that interaction, they both come to the same temperature. So when you put a thermometer in your mouth, like the doctor puts a thermometer in your mouth, that thermometer in your mouth comes to equilibrium, the same temperature as your mouth. Okay? And then we say, and we look at some property, and that tells us what the temperature is. So a good thermometer, what are some properties? Thermometer. One, it has to come to equilibrium quickly. You don't want to have to sit there forever. These mercury thermometers, you usually had to sit there for about a minute or two. Now it takes like seconds. Right? It must not change the temperature of the substance it's measuring. So for instance, if I have a thermometer this big, I can't use that to measure the temperature of a tiny little thing. It's too big. That tiny little thing will come to the temperature of the thermometer, not the other way around. Right? So the thermometer typically has to be much smaller than the thing you're measuring. So for instance, this thermistor that I used when I was an undergraduate, we were measuring the temperature of little crystals about this size. The thermistors were tiny, tiny little wires that we attached to the crystal. They were small so that they would not have a big impact on the crystal. All right, so those two are some of the key ideas. It's come to equilibrium quickly, must not change the temperature. And the third is it has to be precise. And it has to work over some range. Some property has to change significantly. So I cannot take, for instance, a little tube this big and put a little bit of water in it and watch for the water to expand. That's not very precise. The water doesn't expand very much as the temperature increases. But mercury, a tiny bit of mercury in a very thin tube, does expand quite a bit. So that's why it was used for many years. I think they also used some kind of alcohol thermometers as well. They had alcohol in a tube, and that worked all right. The advantage of alcohol over mercury is if the mercury tube breaks, you don't want to consume the mercury. That's not great for you. All right, so that has to have some level of precision. So whatever the property is that's varying has to vary significantly with temperature. So that's what a thermometer is. It relies on coming to equilibrium. By equilibrium, we mean the same temperature as the substance. All right, so let's give this a name. Thermal equilibrium between substance A and B means TA. All right, that's what temperature is all about. Another very important point about temperature. Temperature does not depend on the size of the substance. All right, I have two pieces of chalk here. This has a certain temperature. This has a certain temperature. I put them together. What's the temperature of the two together? What is it? Is it twice the temperature of them apart? Is it? No. Temperature doesn't matter. All right? Temperature does not change with size. Okay? Now, it's true if I have a container of a certain volume and then I change that volume, sure, the temperature might change. All right? But if I have two containers that are identical, absolutely identical, and then I allow them to mix together, I open one and connect it to the other, the temperature doesn't change. All right? So temperature is not dependent on size. It's not dependent on number of particles, the mass, the volume, etc. All right? We call this property intensive. It's a property that does not depend on the size. Can you think of another quantity? It's one of those on the blackboard that is also intensive. Is the total energy of a substance, is that intensive? Is the energy of this plus this, this has energy E1, this has energy E2, what's the energy of them together? Is it the average of the two? What is it? Is it the average of the two? So I want the total energy in here. Has a certain amount of kinetic energy, it probably has some potential energy. There's a certain energy in here. There's a certain energy in here. I put them together. What's the total energy? It's just the sum of the two. Right? It's like the number of students on this side plus the number of students here plus the number of students here. I sum them up. Energy is like that. The energy in your body plus the energy in your body plus the energy in your body is the sum of the energies. So energy is not intensive. All right. Can you think of another quantity? What about volume? Is that intensive? No. All right. The other word is extensive. So far we know energy is extensive, volume is extensive. What about the number of particles? Extensive or intensive? Extensive. What about the pressure? Extensive or intensive? Intensive. So pressure is intensive. TP. Okay? So I think that's most of the quantities. We'll see some others later on. Okay. So that's very important. This idea that temperature, pressure is intensive, and those others are extensive. Every quantity you introduce, every one, we have to look at whether it's intensive or extensive. The key idea of intensive quantities is they are a property of the system that does not depend on how much of the system you have. That's key. All right. How many of you have ever put a heater in your room? Or heated up a room? Did you ever do that? Or you just live in the cold all the time? Sometimes I think you never heat your room up. Do you want to know something? When you heat your room, you do not add energy to the room, believe it or not. That's not what happens. It's right up there. All right? The pressure doesn't change. Does your room get a higher pressure when you heat it up? No. The pressure is the same as the outdoor pressure. Does the volume of your room expand? You live in balloons? No, you don't live in balloons. It doesn't. The temperature goes up. Something else changes. So what you do when you heat your room is you kick out the cold particles. That's what you're doing. Isn't that neat? That's what you do. You don't heat up the room. You don't add energy to the room. No energy is added to the room. The energy that comes out of your heater, all it does is get rid of some particles. That's all it does. The net energy in the room doesn't change. All right? And it's all up there already.